Hi, I'm Charlie Thompson, and welcome to the Lab 13 Topographic Maps pre-lab video. In this lab, let's talk about topographic maps for starters. So, some of the big questions that we ask with topographic maps are, where is it? Often this will be a latitude, longitude. How far away is it? This will often be a distance. U.S. Geologic Survey maps are, unfortunately, everything is feet. We're back to the horrible English system in which we're going to use feet and miles. So how far away is it? Sometimes that'll be feet, sometimes it'll be miles. The question will always let you know. Which direction is it? This will be from 0 to 360. North is 0 and 360, south is 180. I'll talk about how to find direction and use the compass rose to find directions. Azimuth just means which direction. Bearing just means which direction. Azimuth, bearing, direction, they're synonyms. How high is it? This will be elevation in feet. How steep is that slope? There's two ways. What kind of landform? So that's the more sophisticated part. Like all of these, where is it? How far away is it? What's its latitude and longitude? Which direction? How high is it? How steep is that slope, either as a percent or in feet per mile? All of those are objective, right? Those are numbers, and we can say this is true or not true, that the distance from here to there is this many feet. Landforms, you got to look at the contour lines and recognize which landforms go with which shapes of contour lines. That's probably the most sophisticated and maybe the most important thing that we'll do with topographic maps. We will also use Google Earth, which will show us reality or images draped over a 3D surface. So I view Google Maps with Topo Maps draped over them as like the best possible way of understanding what the landscape looks like, which is the whole point of topographic maps, is what does the landscape look like? So the skills that we'll go over today, how to find the location of a place using latitude, longitude, find the distance and azimuth between two places, find elevations of locations, find relief, which is the difference in elevation between two places. It's the vertical distance between two places, and find the slope of a slope as a percent and as feet per mile. So first off, latitude, longitude. If you're using Google Earth, it's incredibly easy. You place the cursor over the location, and then you can read the latitude, longitude, and elevation off the bottom right of the screen, and you're done. Okay, moving along. Find distance. Well, if you're using a ruler, you measure the distance in inches on the map. And if we were in class, we'd have actual plastic rulers. So a sample distance would be 1 and 9/16 inches. We're going to convert that fraction to a decimal. So you divide 9 by 16 and add 1. So 1 and 9/16 inches converted to a decimal is 1.5625. Multiply that decimal, the 1.5625, by the feet per inch on the map. We know the feet per inch on the map because we know what the map scale is. The map scale will be given, or I'll give you information that will allow you to calculate the map scale. So once you know what the map scale is, you can figure out how many feet per inch. For example, a 1 to 24,000 scale map has a scale of 1 inch on the map to 24,000 inches on the ground. So the way scale works with this as a representative fraction, the units on both sides have to be the same. So it's 1 whatever to 24,000 whatevers. 1 inch equals 24,000 inches. 24,000 inches, you just divide by 12 to go from feet to inches. Wait, scratch that, back that up. Divide 24,000 by 12 to go from inches to feet. So we know 1 inch is 2,000 feet. So we've measured 1 and 9/16 inches was 1.5625 times 2,000, 3,125 feet. So using a ruler, you convert the distance in inches to a decimal, multiply the decimal by feet per inch, and that's your distance. You can also, if you had a paper map, paper maps usually have a bar scale. They have a primary scale with large divisions and then an extension scale with smaller divisions, usually a tenth of whatever the larger scale is. So this one has meters and then each of these little bars would be 100 meters. So you take a piece of scratch paper. If you're measuring from A to B, you make a tick mark where A is, a tick mark where B is. We're going to throw that down on the bar scale. So that's 0 to 1. That's 1 kilometer, 2 kilometer, 3 kilometers. And so the way you're going to do this is you're going to put one division on whatever the whole number is until you get the other division, the other tick mark, someplace in the subdivisions. So this one works out that this one fits over the 3. So then we've got 3,000. This would be 800, 950. I would just call this 3,900 and be done with it, because that's 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9. I guess 3,950 meters. Yeah, we probably won't do that because we're not in class. But you might be asked to do that in class. So I thought this was really cool since we know what the ratio is, right? With a 1 to 24,000 scale map, 1 inch equals 2,000 feet. So there's a company that makes rulers, and this ruler is made to use with a 1 to 24,000 scale map. So when you slap this ruler down on the map, you can actually measure directly in kilometers and in miles. So from here to here is 1 mile. Each of these is 1/10 of a mile. So instead of measuring actual inches, you're measuring the distance on the map because they've shrunk down the dimensions to match the scale of the map. So if you know the scale of the map, you can buy one of these special rulers and you'll never have to use these tick marks again. So here's my question for you. On this map, going from here to here is 1 mile. I want to know how many inches is that? And here's the information that you'd need to figure it out. 1 inch on the map equals 2,000 feet on the ground. So if 1 inch on the map is 2,000 feet on the ground, how many inches on the map equals 5,280 feet on the ground? I'd like the answer as a decimal. That would be swell. Decimal, I don't know, maybe to 3 decimal places. Depends on what the answer is. You do the rounding. 5 points extra credit to the first student to email me with the correct answer. How many inches on the map equal 5,280 feet on the ground given a 1 to 24,000 scale map? So to find distance using Google Earth, measure the distance in feet using the measure tool, write down the distance in feet, you're done. Map scale. Map scale is very important. When we're talking about the scale of maps, it's the ratio of the size on the map to the size on the ground. Big scale maps have a lot of detail of a small area. Like a 1-to-1 scale map would be the biggest scale map. Well, that would be, the map would be the same size as Earth, right? I mean, I suppose you could do it even bigger than that, but a 1-to-1 scale map would be the biggest scale. That would be a map that would be the size of the planet. Small scale maps have small detail of a large area, so like a classroom map of the world. Those are about 1 to 20 million. If it's about 6 feet wide and it's showing the entire world, the scale on that map is about 1 to 20 million. That's great if you want to see the whole world. But if you just wanted to see, for example, American River College, you'd probably want like a 1 to 5,000 scale map. So the smaller the number, the denominator, the smaller the denominator is, the larger the scale of the map. And the way I've started thinking about it this semester is the larger the scale of the map, the larger the map would be of the Earth, right? So a 1-to-1 scale map of the Earth would be as big as the Earth. A 1 to 20 million scale map would be 1/20 millionth of the size of Earth. It'd be about 6 feet wide. There are 3 ways that we will use to show map scale. There's a representative fraction, which you've seen, 1 to 24,000. There's a graphic scale, which you might have seen, and there's a written scale. So the representative fraction, the units on both sides are the same. It doesn't matter what the units are. 1 inch to 24,000 inches, 1 foot to 24,000 feet. Both sides have the same units. Graphic scale. You've seen this before, primary, extension scale. Good thing about graphic scales is if you're going to enlarge or shrink the map, as the map gets blown up, the graphic scale gets blown up the same way. So if you had like a 1 to 24,000 scale printed map, and you enlarged it so it was twice as big, it would be a 1 to 12,000 scale map, but it would still say 1 to 24,000, so that would be wrong. But if you had a graphic scale and it got blown up twice as big, the graphic scale is twice as big, so you're still good to go. A written scale has different but common units on both sides. So 1 inch equals 1 mile. That's an example of a written scale. 1 centimeter equals 1 kilometer. That's an example of a written scale. I mean, all the scales are written down, right? But written scale has different but common units on both sides. So there we've got a written scale, 1 inch equals 4 miles. We've got a representative fraction, 1 to 250,000. And then we've got some bar scales. Small scale, the larger the denominator, the smaller the scale. Large scale, 1 to 24,000. That's the scale that the entire United States, or at least the lower 48 states, has been mapped at with topographic maps, 1 to 24,000. All right, so there's the representative fraction, and here's a written scale. Back in the day, most of the U.S. was surveyed, the old school maps are 1 to 63, where 1 to 63,360, where 1 inch equals 63,360 inches, which is a mile. There's 63,360 inches in 1 mile. So the magic of the 1 to 63,360 is 1 inch equals 1 mile. Those maps have been replaced with the 1 to 62.5 scale. So, map scale calculation. Map scale, as you know, is the ratio of the size on the map to the size on the ground. So if I gave you a world globe that was 61 centimeters in diameter and asked you what the scale of the map is, you'd need to know that Earth has an equatorial diameter of 12,756 kilometers. So the scale of the globe is the ratio of 61 centimeters to 12,756 kilometers. So the first thing we want to do is get both sides of the equation into the same units. And then we want to get the denominator down to 1. To find elevation, we're going to use contour lines and maybe sometimes spot elevations. Relief, again, is the difference in elevation between two locations. Sea level is 0. My house is at 52 feet. So the relief between my house and sea level is 52 feet. Contour lines. So now we get into the meaty stuff. Contour lines are printed in brown. I've added this blue line. They don't use blue on topographic maps. They use blue for rivers. They don't use blue for trails, but I thought it stood out more. They use black, but I don't remember why I wanted to emphasize that trail, but I did. So these brown lines, 6,600, 6,800, those are contour lines. Each contour line connects points of equal elevation. So if you walked around this contour line and you had a GPS unit, you would see that you were always exactly 6,600 feet above sea level, 6,800 feet above sea level. If you're right here where the X is, that's a point elevation. That would be 6,907 feet. That's a spot elevation. The newer maps, for some reason, don't have those. Well, it's not some reason. There's a very good reason. The good reason is that the new maps are more accurate than the older hand-surveyed spot elevations. The contour interval is the vertical difference in elevation between two adjacent contour lines. So the vertical distance, for example, between the indexes is 200 feet. 6,600. 6,600, 6,800. So the next one down should be 6,400, and the next one down would be 6,200. Every fifth contour is thicker and darker and should have a number attached to it at some point. Those are index contours. So the index contours are every fifth, 1, 2, 3, 4, 5, index 6,800. To find the contour interval, if it's not given on the map, on every USGS topo map it's given to you, but if I just take a chunk out of it, if I take a selection, it might not have the contour interval. So you take the difference in index contours and you divide that by 5. So we've got a 6,800, we've got a 66. So the difference between those is 200 feet. 200 feet divided by 5, 40 feet. So each of these lines going uphill, and you can tell you're going uphill because the lines are they're closed circles and they're getting smaller and smaller and smaller as you're going uphill. This is 40 feet higher, 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 40 feet higher. So contour lines, where they're close together, it's steep. Where they're far apart, it's flat. Like down here in the valley, there's like one contour line, two, and here they're really close together. Here they're very close together. So that's a vertical face. That's a cliff. That's a cliff. In fact, right there, panoramic cliff. That's a clue. Contour lines only touch where there's a cliff. So even though Half Dome is vertical, the contour lines aren't touching there. Parts of Glacier Point, vertical or almost vertical, but still not touching. Contour lines never touch and never cross, or rather, they only touch if there's a cliff. Contour lines never cross. Contour lines going upstream, so we're going up, up, up. The contour lines make a V or an A pointing upstream. Alligators always swim upstream. Alligators always swim upstream. Oh yeah, this is Lake Shasta. And I thought, it's a great example of that is lakes as they're draining. So as the lake's draining, these are like contour lines. It's where the lake elevation was for a while and the wave action made these marks. I really am bummed that there's not more detail right here, because here the lines should be close together and here the lines should be far apart. Here the lines should be far apart because it's flat. Here they should be far apart, but we can't really tell. But you can see that the contour lines make a V pointing upstream. Contour lines crossing stream valleys form a V pointing upstream. Hilltops are closed circles, Sentinel Dome, whatever that is, that, Mount Broderick, Liberty Cap, those are all examples of hilltops. Concentric closed contours show a hill or summit. Elevation of Sentinel Dome. So this doesn't have a spot elevation. Like I said, the older maps do have little X's or triangles or an X with a BM by it for a spot elevation. The newer maps have actually illuminated the spot elevation. So the top of a hill is a half contour line higher than the last contour line. So the contour interval is 40 feet. The last index was 8,000. This is 7,800. This is 8,000 feet. So it's 1, 2.5 contours higher. So the summit of Sentinel Dome is 8,100 feet. The unnamed hill south of Sentinel Dome, contour interval is 40 feet. The last index was 78. Again, it's 2.5 contours higher. 1 contour, 2, 2.5 is 100 feet. So the elevation is 7,900 feet of the top of that hill. Oh, what if it's a depression? What if it's a caldera? What if it's the cinder cone where it actually dips back down? If these were just regular closed circles, we would assume that that would be the summit and you'd be going up and up and up. But actually these tick marks are called hachur marks, Gesundheit, hachur marks, and they point down slope. Not only do they point down slope, but they have the same elevation as the last contour line. So if this was 68, this is 68.40, and now we're back to 68. So they almost are never marked, but because it's an index, we know that it's 68. If it wasn't an index contour, we would know that it would be 68.40, right? Because this is 6,800 feet, this is 68.40. This is an index, so it went from 68 going up, going back down to 6,800 also. And then that's going to be 40 feet lower, 40 feet lower, 40 feet lower, and then half a contour interval lower. So the first hachur line is the same elevation as the last contour line that you crossed. Like I said, this is an index, that's an index, so we know it's 68. And we know the bottom of the caldera is going to be 3.5 contour intervals below 6,800 feet. That's 68. We go 1, 2, 3.5. So 3.5 times 40 is 140. So we know that the elevation at the bottom of the caldera of the cinder cone has to be 6,660 feet. Landforms. Yeah, so I stole all of these from the Army Field Manual on Land Navigation because the Army is really good at explaining things. So a ridge line is the connection. It's a ridge. It's what connects mountain peaks. So peak, ridge, peak. Hill is shown by closed concentric contours. The smallest circle is the hilltop, and that's going to be, again, half a contour interval higher. A saddle is a dip, so that's a mountain peak, that's a mountain peak. In between is going to be a saddle. A valley is going to be shown, so we actually know, I was going to say we know which way is up, right? Or we should, because we should be pointing uphill, so that's making an A going uphill, that's making an A going uphill, that's making an A going uphill. That's a very confusing example. A ridge, instead of circles, it's going to be an oval because it's not circular, it's more of an oval shaped. Contour lines forming a ridge tend to be U-shaped for a ridge line. A depression with hachure marks, again, pointing down. The little tick marks are pointing down. So whatever this contour line is, that would be the same elevation. Contour line, so that would be going up. This would be going down. A draw is like a small valley. So this is going, let's see, going up, going up, going up, going up would be going up a small valley. And again, making a V, the A points, the top of the A points upstream. Alligators always swimming upstream for a draw. A spur is a little ridge. So that's a ridge, draw, ridge, draw, ridge, draw. So that would be a draw. That's a spur. That's a draw. That's a spur. A spur is a ridge coming it's a ridge coming off a ridge. A spur is a short ridge coming off of a larger ridge or higher ground. Spur. Cliff, it's vertical. The lines are touching if it's vertical. Oh, this is pretty good. I like this. It's a larger, so we've got hills. We've got hills. I would say that this is, we're looking at a ridge from here through here. 3, they're saying that's a ridge. That looks more like a spur to me. 6 is a draw. 6 is a draw. 7 is a spur. 5 is a depression. You don't need to worry about cut and fill, but that's pretty good. Oh, 4, they're showing the 4 is a saddle. That makes more sense. So you're actually going down and then back up and then down and then back up. Ooh, and that's it for this video. I wish you great enjoyment with your Topographic Maps lab. I hope you have fun. I hope you enjoy Google Earth. I hope you can figure out where you are and how high you are.